Okay, I believe we are ready to start. Are we? Okay, thank you for closing the door. So hello, everyone. Welcome again to Warsaw University Astronomical Observatory Tuesday seminars. Is everything okay, Mariusz? Okay, I assume so. Okay, very good. Okay, so today we have a speaker from the US, Ilaria Caiazzo, who is a member of the ZTF group. We will know about this group. Ilaria is from Italy and did her master in Milan, working on pulsars. And then she moved to Canada, where she did her PhD, working on polarized emission of neutron stars and black holes in X-rays. And now she's involved in NASA and IX-PIE space mission, collecting first observations in X-rays, which sounds actually very exciting. Now she's a member of Caltech community and ZTF group, where she joined the variable stars group. And she's going to tell us about ultramassive magnetized double-phased white dwarfs, exotic white dwarfs in ZTF and Gaia. Ilaria, please.
Thank you very much for the introduction, and thank you for having me here. I'm very sorry that I cannot actually be in Warsaw, and I apologize if I'm a bit slow in talking, but I haven't had coffee. I only had time to make decaffeinated tea, and it's 7 a.m. here. But yes, I'm very excited to tell you about the work that we've been doing with the ZTF Variable Stars group, finding exotic white dwarfs. But before I get into the exotic one, let me just quickly start from the typical white dwarf that we all learned in kindergarten. It's typical white dwarfs are the size, have the mass of about half of the sun, 0.6 solar masses, and the radius much smaller, closer to the radius of the Earth. And also, the typical white dwarf has a core that is made of the ashes of helium burning, so mostly carbon and oxygen. And then the atmosphere of the white dwarf is stratified because of the strong gravity. And the surface layer, you only have the lightest element present because all of the heavy elements sink very quickly. And so the typical spectrum of a white dwarf is, only shows absorption line of hydrogen. As you can see here in the optical, these are all the Balmer lines. And so we know a lot about the typical white dwarf. We've studied them very well. We know how they cool, and we know how they evolve. But there's still a lot of open questions regarding white dwarfs, and they all revolve around the atypical ones. And they all have big implications for many other fields of astrophysics. For example, one of the questions that I'm very interested in is what is the origin of magnetic fields in white dwarfs? Because we know that about 20% of white dwarfs are magnetic, and they have fields that range from just a few tens of kilogauss to a billion gauss. So we're talking about several orders of magnitude in difference. And so we still don't know why some white dwarfs are magnetic and some aren't, or where this huge diversity in fields come from. Another question that I'm very interested in is where the polluted white dwarfs come from, because as I told you, metals sink very quickly in the atmospheres of white dwarfs. However, some white dwarfs show metal lines in their atmospheres or disks around them, debris disks around them. There's all this question of how did they get there, all of this planetary material, and what happens when to a star system when the center star dies. And then there's not only metals or hydrogen, there's lots of other compositions in the atmospheres of white dwarfs. For example, there's helium-dominated white dwarfs, which we think don't have enough hydrogen, and so we only see the helium underneath. But the other interesting thing is that white dwarfs don't stay in one state their whole life. There's a spectral evolution of white dwarfs. For example, hydrogen white dwarfs can transform into helium white dwarfs. And there's also something we're not sure how that happens. And then, of course, there's all of the questions related to exploding white dwarfs. For example, what is the origin of type 1a supernovae, and what is the maximum mass for a star to become white dwarf and to not explode in a core collapse supernova? So lots and lots of open questions, and I'm going to talk about at least some of them today. But why this has been open question for a long time. However, this is a great moment to study white dwarfs because there's so many missions that are really revealing and really initiated a stellar revolution because they're changing the landscape of stellar studies and of white dwarf studies. And of course, Gaia, it's been amazing, especially for white dwarfs, and I'm going to show why. And then all of the high cadence time domain surveys that you know very well, they've really been changing the way we study the sky because we're starting studying the dynamic sky. And then there's the spectroscopic surveys coming up. There's SDSS-5, for example, which is going to reveal spectra of 300,000 white dwarfs. And then, of course, LISA with merging white dwarfs, and even JWST can tell us a lot about white dwarfs. And since every talk now needs to have a JWST picture, I'm gonna show you mine. This is actually a program that we just received the data like a couple of weeks ago. So this is just what came down from the telescope. We haven't done much work on it yet, but it's a program to look for white dwarfs in globular clusters that have infrared excesses, and so that have debris disks around them. And this is to study if, are there polluted white dwarfs in globular clusters like there are in the field? Did planetary system already exist in these very ancient and metal poor populations? So stay tuned because this is a project that just started, but I just wanted to show you that JWST is also, there's many programs regarding white dwarfs with JWST, including this one. Then let's go back to why Gaia has been really revolutionary for white dwarfs. As you know, the way, and it's been really good because it allowed us to find many white dwarfs in a much simpler way. Because as you know, white dwarfs are blue, dim objects. But if you don't have the distance, you cannot really distinguish from blue stars that are farther away. And so before Gaia, most of the white dwarfs were identified through spectroscopy and mostly through the Sloan spectroscopic survey. While after Gaia, we have not only the colors and the magnitudes, but the distance, precise distance of billions of stars, including white dwarfs. And so if you look at the HR diagram, the Gaia HR diagram, then the way you find white dwarfs, when you can plot the absolute magnitude on the y-axis, then they're the ones in this lower left corner. It's very easy to find white dwarfs now. And so you can see the difference between before Gaia and after Gaia in the number of white dwarfs that we have. So before Gaia was about 30,000 white dwarfs, mostly from SDSS-5. You can see they're mostly in the north. But after Gaia, we have a much more uniform sample all over the sky. Not only more than 10 times more white dwarfs, but also a much, as I said, uniform sample, much deeper sample. This was really focused mostly on bright objects, and also SDSS was really built to find galaxies, not white dwarfs. So it was a very strange sample that we had before. Now we have a very rich and uniform sample of white dwarfs. And when you have, when you increase by an order of magnitudes the number of objects that you have, two things happen. you can start you can start counting them, and so making volume limited samples, for example, because also we know the distances, but also we can start finding the rare objects. And this is appeared immediately. So these are just giving you an example of two papers that came out just right after Gaia DR2 was released. And these regard massive white dwarfs, because of course massive white dwarfs are much rarer than normal white dwarfs. Here again is the HR diagram. And this is the main sequence of white dwarfs, which is about, white dwarfs are 0.6, 0.7 solar masses. And as you go to more and more massive white dwarfs, they become more and more rare. And that's just because of the initial mass functions of the stars. It's very steep. However, we immediately had so many more massive white dwarfs just because of Gaia. And we could immediately see, for example, here we have where they pile up because of core crystallization. So here they are cooling down and they pile up here because that's where they crystallize. And so they start cooling much slower because of the latent heat of crystallization. And these was just papers that we could do because now we had lots and lots of massive white dwarfs and we knew their distances, etc. And so I'm going to also tell you about some work that a graduate student at UBC that I co-supervise with Mikhail has been doing using only Gaia on massive white dwarfs. Here again, you can see the HR diagram, the Gaia HR diagram for white dwarfs. And here in green, these are cooling curves. So they're models of cooling white dwarfs of different masses. And here you can see that these were the most massive white dwarfs stay. We went from 0.95 to about 1.3 solar masses. And so what the student did, what Lisa Fleury did, was to assign a mass and an age to all of the white dwarfs using different available models for white dwarfs. And these are all of the white dwarfs within 200 parsecs of the Earth. And she plotted them just using mass and cooling age. And you can see that there's a huge accumulation. So if the models were right, and if the star formation of white dwarf, if the formation rate of white dwarfs was constant, you would see a uniform color on this plot. But you see a big accumulation here of white dwarfs, which is not crystallization, because the crystallization that I showed before happens down here, so it's much more subtle. So there's an excess of white dwarfs just by counting them between 2 and 5 gigayears ago, of white dwarfs that formed between 2 and 5 gigayears ago. But if you look though at the star formation rate, for example, this is another result from Gaia, in which you can see that the star formation rate was going down in the galaxy, 10 billion years ago, except coming closer. However, there is an excess, a bump in star formation rate between 2 and 5 gigayears ago. And this was found using main sequence stars and evolved stars, not using white dwarfs. And so we are finding the exact same thing in white dwarfs. So we're kind of confirming these star formation rate results from main sequence, but using white dwarfs, which are very precise because we can know their cooling ages very nicely. And so this was a very nice result that we just used using Gaia, no follow-up or nothing, just by counting white dwarfs. And another thing that we found out is that if we divided, so here we're showing the same sample, but we divide them in different mass range of the mass of the white dwarfs. And in orange is what you would expect from the star formation rate, from the one that I showed before. And in blue is what we actually observed from the white dwarfs. And you can see that there is a very nice agreement in the two lower mass bins. So we're finding exactly what we expected. Oh, sorry, this is the cumulative distribution. So each point shows how many white dwarf below a certain cooling age we have. And so these two mass beams really reflect the distribution that we expect from the star formation rate. But when we go to the higher mass beam, above 1.1 solar masses, then you can see that the observed distribution is way more uniform than what you expect from star formation rate. And this is something that we expected, but it's also very nice to see it so clearly. And that's because in this mass range, that's when the white dwarfs that come from single stars become more and more rare because of the initial mass function. But there are another type of white dwarfs that become more and more common, which are the white dwarfs that are formed by the merger of two white dwarfs, by double white dwarf mergers. And that's because if you think about this typical white dwarf mass is about 0.6 solar masses, the typical double white dwarf merger remnant is about 1.2 solar masses. So here we have a contamination, a very big contamination of merger remnants with respect to white dwarfs that are born from a single star. And those merger remnants are changing I'm changing the distribution because they have a delay. You're not forming the white dwarf, the 1.2 solar mass white dwarf directly. You have to form two white dwarfs first, and then they have to spiral and merge. And so those introduces a delay that is diluting this distribution due to the star formation rate. So from this, we could figure that in this mass range, we have a large fraction, more than 50% of the white dwarfs in this mass range might come from mergers. Go check her papers. She's actually graduating soon, and she's going to be looking for jobs. So I'd also like to show something else that we can do with Gaia before we move on to the merger and exotic white dwarf section, which is to look for white dwarfs in clusters. Because with Gaia, we don't only have very good distances, but we also have the motions of the stars in the sky. And this is very good to find objects that are members of open clusters. And that's because you can find them, the clusters in the past were found visually mostly, if the stars were all in the same part of the sky, but for now we can also see if the stars are all at the same distance, and also if they're moving together in the plane of the sky. And so you just look at the parallaxes all of the stars to find mergers, to find cluster members, but also you look at their motions make sense, so in proper motions in the sky. And this is very useful if you want to find white dwarfs that are members of clusters. And finding white dwarfs that are members of clusters is very useful because this is, for example, 3 different clusters shown here, and the black clusters, which I think is ACC 47, as a white dwarf. And we can get the age of the cluster by seeing the main sequence stars that are getting off the main sequence, looking at their masses and their brightness. That tells us the age of the cluster. And also we can know the age of the white dwarf just by looking at its magnitude and color. That will tell us the temperature, and therefore will tell us the age of the white dwarf. And so by subtracting the two, we can figure out for each white dwarf found in cluster, what was the progenitor mass, the mass of the progenitor star that created that white dwarf. And that's something that with my group at QBC, we have been working on just using Gaia. And we found lots and lots of white dwarfs in clusters. that are constraining this upper part of the initial final mass relation, because this is the initial mass of the progenitor star, and this is the final mass of the white dwarf. And you can see that we are trying to constrain this upper part of this relation. And we have been finding many new white dwarfs, and this is all work in progress. And this is very important, not only because we want to figure out what's the maximum mass for a white dwarf, for a star to become a white dwarf, but also because this relation tell us a lot about the physics of evolved stars and of stellar winds, of convective overshoot. So this is another thing that we can do just using Gaia. And also another cool thing is that a lot of these white dwarfs that we have been finding in clusters, they turn out to be magnetic. And this tells us, so these clusters are very, very young. They're maybe 100, 150 million years old. And so they didn't really have time to create two white dwarfs that then would merge. And so we know that at least some magnetic white dwarfs come from single star evolution, which was still an open question before we found these white dwarfs. But we know that some white dwarfs, we know that some white dwarfs do come from mergers, because we saw that in the Gaia sample. And we know that merger remnants should be magnetized, and that's because when you take two white dwarfs and you merge them, there's very strong dynamos that develop in the merger that should enhance and create very strong magnetic fields. So we do expect some magnetized white dwarfs out there to be the remnants of a double white dwarf mergers, and we expect them to be mostly in the high mass range of white dwarfs, and we expect them to be highly magnetized. But how do we find out? How do we find them, and how do we distinguish them from white dwarfs that come from single stellar evolution? By one last thing, which is we do expect white dwarfs that come from a merger to be rapidly rotating because of the conservation of angular momentum of the binary. Some of that orbital angular momentum get transferred to the final merger remnant. And so if you have something that is highly magnetized, their emission from the surface is often not uniform. You might have hotspot or gradients in temperature. And if there's something that is emitting not uniformly and it's rotating, you expect them to be photometrically variable, because, for example, the hotspot might come in and out of the line of sight. And so these are perfect objects to search with the Zwicky Transient Facility. And I think you know a lot about ZTF, so I will not spend too much time on this, just telling you that, as you know, ZTF is a synoptic survey run at Palomar Observatory by Caltech in a big collaboration of other institutions. And it was designed to look for transients, hence the name, supernova, TD, but it's also a great, that is me when I finally got to go there in the spring. I was very happy because, because of the pandemic, it was the very first time I could go there after years of using the data. But as I was saying, ZTF is not only a great transient facility, but it's also a variable stars facility. And that's because it takes images of the entire northern sky every couple of days, because it has a huge field of view, 47 square degrees. And so it can really reach very high cadence of, like, again, once every couple of days. And so we quickly accumulate hundreds of epochs for each source. And when you have hundreds of epochs for each star, you can start looking for periodic stars and periodic white dwarfs. So stars that change with the, sorry, again, 7 a.m. It starts to change photometrically with certain periods. And of course, it's not that easy. There's been some amazing software developed by the Variable Stars group. Shemek, that is now there with you, I guess now it's in Chile, but is there at Warsaw. He developed a great pipeline for force photometry, and Kevin Burge developed period searching algorithms. But thanks to them, then now we can search for period all the stars that are observed in ZTF. And this is exactly what we did for searching for white-dwarf mergers. As I told you, we focus mostly on the massive stars, on the most massive white dwarfs, which are down here. And so we search them in ZTF for periods. And then, of course, we need to follow them up with a higher signal to noise photometry instrument, a fast photometry instrument, for example, Chimera on the 200-inch telescope at Palomar, because sometimes the period turn out to be maybe twice of what we found. And then to figure out if they are magnetic, then we need to take spectra of this white dwarf, and even better phase resolve spectra. And for this, we use Keck, the Keck telescope Mauna Kea, which is a very, very powerful telescope, and it allows us to take maybe 30 seconds exposures on 20th magnitude white dwarfs. So really looking at how the magnetic fields change on the surface of the white dwarf. And just let me tell you very briefly how we found out that these white dwarfs are magnetic. So I showed you before the typical spectrum of a white dwarf with the absorption Balmer lines. So these are the absorption lines of hydrogen. So what happens to the spectrum of a white dwarf when there is a strong magnetic field? In the case of hydrogen, let's start from the case of hydrogen, which is the simplest one. The high magnetic field lift the degeneracies in the levels of the hydrogen atom. Now, if you remember, each level of the hydrogen atoms is 3 quantum numbers, N, L, and M, and all the energies are degenerate in those quantum numbers. But if you have a magnetic field, then if you have different M's, then the energies are slightly different. So for example, this is the Balmer series is all the jumps of the electron between the levels n equal 2 to n equal 3, for example, or n equal 4. But if you introduce a magnetic field, that jump between 2 and 3 is different if you have delta m equal +1 or -1 or 0. And so instead of having one absorption line, you have 3. As you can see here, so this is the Zeeman splitting. And so, for example, this is H alpha. Instead of seeing one absorption line, you see 3, because it's delta m +1, delta m -1, or delta m equals 0. And the higher the magnetic fields, the stronger, the farther apart are the energy levels of the different components. And so by taking a spectrum of a magnetic white dwarf, we can not only see that it's magnetic, but we can also estimate the average magnetic field on the surface of the white dwarf by looking how far apart are these 3 components. And that is true for intermediate magnetic fields, between 1 and a few tens of megagauss. As you can see here, this is 2 megagauss, 11, 32. But if you go to higher and higher magnetic fields, it becomes a bit more complicated. And this is what I'm showing here on the right. You have, this is again H alpha, H beta, and H gamma, 3 different transitions of hydrogen transitions. And you can see this is the magnetic field, starting from a megagauss up. And you can see at lower magnetic field, you have the splitting still. But as you go to higher and higher fields, more degeneracies get lifted, degeneracies get lifted, and so you start having more and more components. until at a certain point, the hydrogen atom is not spherical anymore, so you cannot use spherical harmonics. It's becoming more and more cylindrical, and you have to start using variational techniques to study the transitions. But what happens is that the energy shifts very quickly with magnetic fields, and so since you're not looking at one strength of the magnetic field, but you're summing over the entire surface of the white dwarf, where you expect the magnetic field to vary, what happens is that often the spectra of highly magnetized white dwarf become almost featureless, because you can see, because the features change too quickly with the change of magnetic field, and so they get completely washed out. Unless it's one of these features, the stationary lines, these are called, they go to a minimum or a maximum in energy with magnetic field. And that's how we can often identify the magnetic field. The very strong magnetic field by dwarfs is by recognizing features at these particular locations. So this is what we did. We took a lot of spectra of this this rapidly variable white dwarfs that we found in ZTF. And we actually found out that most of them were magnetic. And this is the first one that we looked at. It really stood out because it was extremely blue, so extremely massive. It was one, as you can see here, the Gaia HR diagram. It was one of the bluest objects in Gaia. But also because it has an extremely small period of 7 minutes. So normal white dwarfs rotate with periods that go from a few hours to a few days. Those are like normal rotation periods for white dwarfs. So 7 minutes is very, very, very small. And here you can see the ZTF light curve, and this was the Chimera light curve from the same object. And then we got a spectrum of the white dwarf. And now I was showing you before those plots with all of the magnetic fields changing. This is exactly what this is again, showing that we were able to identify these very broad and shallow features of the white dwarf as a magnetic field, as due to the magnetic field of about 800 megagauss, which is very, very, very high. It's one of the highest magnetic field found on a white dwarf. And so this was like already, it was rotating very fast, 7 minutes, extremely magnetized. This is really the poster child for the merger remnants for white dwarf. But we also wanted to figure out the radius for these white dwarfs. So we got UV photometry to constrain its temperature. And from the SED, we were able to estimate that the radius is about 2,000 kilometers. And so, as I told you before, white dwarfs are usually the size of the Earth, normal white dwarfs, while this one is closer to the size of the Moon. As you can see here in this artistic impression that we got done with this white dwarf. So it's being, so small, it means it's extremely massive. It's probably the most massive white dwarf known. And so depending on the composition, the mass is about 1.35 solar masses, and probably the closest found closer to the Chandrasekhar mass. And it's so dense. This white dwarf is so massive and so dense, it's so small, that if you, of course, this is what I'm showing here, is like the radius of the white dwarf and the mass of the white dwarf that you can get from the mass radius relation, assuming different types of compositions for the white dwarf. And so this red one is for the mixture that you expect from carbon burning, because at such high masses, you expect in the evolution of the white dwarf carbon burning to have happened, and so the core of the white dwarf to be made of magnesium and oxygen and neon mostly. So what's going on is that so these are like the different mass radius relation, but here in black I'm also showing where you expect the electron capture to start happening in the core, because this white dwarf is so dense in the core that similar to neutron stars when they form, there is some neutronization going inside the core, which is sodium nuclei are capturing electrons and transforming them and the proton into neutrons. And so this is probably the only white dwarf known where we expect something like this to happen. So yeah, there's like some electron capturing going on. And this is also very concerning for the full white dwarf, because white dwarfs are kept up by electrons. And so if electrons are continually being captured by nuclei, then this structure of the white dwarf has become more and more unstable. And so the white dwarf needs to shrink to obtain a pressure enough to keep up the white dwarf against gravity. And so this white dwarf might be actually in a metastable stage. So right now, if we just calculate how much sodium is in the center of the white dwarf, the white dwarf should be stable, so it shouldn't collapse anytime soon. But since heavy elements tend to sink into the core of the white dwarf, sodium might be still sinking into the core of the white dwarf, and if enough sodium gets into the core of the white dwarf and it captures enough electrons, then the white dwarf might collapse in the future. And of course, what would happen in that case is we don't know. It would depend on the dynamics of oxygen burning, but it could either explode in a thermonuclear supernova, so become a type 1a supernova, or collapse to a neutron star, similar to what's theorized for accretion-induced collapse, except that this guy is not accreting anything, it's just extremely massive and on the verge of collapse. I don't think this object is actually going to collapse because it might crystallize before then, so the core might freeze, and so there will be no more sodium getting into the core. But if it happens, I think it's very interesting because this object is very close by. It's only 40 parsecs away. So it means that this type of type 1a or neutron stars born from a white dwarf, they're actually very common. So this would make up for a large fraction of either type 1a's or neutron stars formation channel. And again, so this was only the very first one that we looked at. And now we have a big sample of rapidly rotating, massive and ultra magnetized white dwarf that is coming up to be a big sample of merger candidates. And right now it is still work in progress, so I'm just showing some of the characteristics of the white dwarfs in my sample. Of course, they're mostly massive because that's where I focused my searches. But they have a big range of temperatures, big range of magnetic fields. They go from very small fields up to a gigagauss for some of them. But all of them are rotating very fast. All of them below 2 hours rotation period, and most of them below half an hour rotation period. So these are really very hard to make with single star because of this very high frequency, and they're really high confidence candidate mergers. And so what do you do when you have a sample of bona fide merger remnants? You can start studying the properties of the remnants and see if they evolve differently from single stars, white dwarfs, for example, what's their compositions, and it can start constraining this delay time between the formation of the white dwarf binary progenitor and the merger. Also, if I can get a very good selection, completeness for my sample, and understand very well all of the selections effect that come from finding them in ZTF, I can start constraining the white dwarf merger rate in the galaxy. And that will inform us on how many close white-dwarf binaries are there in the galaxy, so telling us also how many we will find in LISA. But also what's the contribution of double white-dwarf mergers to the supernova type 1a rate, because I'm finding the ones that just escaped the supernova, they were just not massive enough to explode. If the two white-dwarfs were slightly more massive, they would have exploded in type 1a supernova. And then, of course, one question that I'm very interested in is the origin of magnetic white dwarfs. And so if these are mergers, how do they differ from the ones that we found in clusters, for example? And what does this tell us about how magnetic fields are generated in white dwarfs? And so I have just a couple of more minutes. I also want to show you, so this is, again, the beginning of our search. That was the very first object that I showed you. Now we're putting this search together. And so I think there's going to be a lot of more things coming out of the sample. But I also like to show you another exotic class of white dwarfs that we found somewhat serendipitously while we were looking at this sample of rapidly rotating white dwarf. Yes, please do not tweet, take pictures, because it is still in review. One white dwarf that we found was, again, you can see here a very massive white dwarf, a very rapidly variable white dwarf. Here you can see the beautiful light curve from hypercam. It is very sinusoidal, and it's a 15-minute period. And but when we got the spectrum of this one, we didn't see any magnetic field. So as you can see, in blue, I'm showing the hydrogen line, and in red, I'm showing helium lines. But there's no splitting, and the lines are in the place where they're supposed to be. So there's no obvious magnetic field in this object. And so it kind of looks like a helium, a mixed helium-hydrogen atmosphere white dwarf. But this is the spectrum taken in long exposure, so over many periods. But when we looked at the phase resolved spectrum, so each of these spectra are taken at a different phase in the white dwarf period, the white dwarf rotation period, you can see that, for example, the hydrogen lines are strong at phase equal 1. You can see them here and here and here. But if you go to the opposite phase, 0.5, they completely disappear. You see, they're not there anymore. While on the other hand, the helium lines, which are in red, are very strong at phase 0.5, and they completely disappear at phase 1. So this is a double-phased white dwarf. As it rotates every 15 minutes, we can see the two phases. And on one side, it's completely hydrogen, and on the other side, it's completely helium. It's quite an exotic object. And for this reason, we called it Janus, like the Roman god with two faces, which is also the Roman god of transition. It's the god of transition, which I think it's a very fitting name, because Janus might be a transitioning white dwarf. So as I told you at the beginning of the talk, the atmospheric composition of a white dwarf might change over its lifetime. And indeed, we know that some helium white dwarfs transition to having a hydrogen-dominated white dwarf, and then back to having a helium-dominated white dwarf. And in this range of temperatures between 50,000 and 30,000 white dwarfs, this is called a dB gap. dB are the helium white dwarfs. And that's because there's very, very few helium-dominated white dwarfs known in this range of temperature. But if you go below 30,000, the number of helium-dominated atmospheric white dwarfs go up by 3 times. So we know that some hydrogen-dominated white dwarfs are bound to transition to helium-dominated white dwarfs going below that temperature. And the explanation is that the hydrogen, hydrogen floats, right? Because it's the lightest element and this gravity is very strong on the surface of the white dwarf. So what happens in this temperature is that in this temperature range, that if you have even a tiny, tiny amount of hydrogen, it will float and cover the entire surface of the white dwarf, like an ocean on a mountainless planet. You just need very, very, very small amount of hydrogen to cover the entire thing. And however, when you hit this temperature, this is when in the helium layer, right below the hydrogen, convection starts being very, very strong. And so convection in the helium layer can break this clean layer of hydrogen and dilute it, mix it with the helium, and so it completely disappears because the helium is much more. But for this to happen, of course, the hydrogen needs to be a very, very, very small amount. We are talking about 10 to the minus 15 or 10 to the minus 14 solar masses of hydrogen on the surface of the white dwarf. And so this was the explanation for this transition, right? You have like this thin layer, and then you have the convection starting and the thin layer get destroyed. And so that's why we start seeing more and more helium white dwarfs below 30,000. And Janus is right at that temperature. So we got UV photometry, and also we have pulsar photometry. And so we we looked at the temperature at the two different phases, and they both make sense for the white dwarf to have about 35,000 degrees temperature, effective temperature. And so Janus is really there at that edge, at the red edge of the so-called dB gap. So what's going on is that it might be transitioning, but on top of that, we do need something to explain why we have hydrogen only on one side and helium only on the other side. I mean, white dwarfs are fluid. It's very hard to create such a striking difference. And so we do think that there might be a very small magnetic field on the surface of the white dwarf. I'm saying small because we don't see it in the spectrum, so it has to be less than a megagauss. But but on one side, it's strong enough to inhibit the convection. So there's no convection in the helium layer because of the magnetic field. But on the other hand, on the other phase, the magnetic field is not strong enough to inhibit convection, and so the helium layer has destroyed the hydrogen. So on one side, the hydrogen survives, and on the other side, the hydrogen is destroyed by the convection in the helium. So that could explain why we see this double phase behavior. Another possibility is that there could be a hydrogen ocean. So if you have very, very, very tiny amount of hydrogen on the surface, and you can create a sort of a pool on one side, then all the hydrogen can float to that pool, can be fused to that pool, and so you create some sort of a hydrogen ocean on one side. And again, you can do this if you have a weak magnetic field on the surface that has a difference in strength between two different sides. Because where you have a stronger magnetic field, then you have a higher magnetic pressure and a lower gas pressure. And so you create some sort of a pool where the hydrogen can diffuse and create the hydrogen ocean. So this could be another alternative that doesn't involve convection, for which we have this very strange behavior. Again, this is also very much at the beginning. We just have the paper now in review. But I think I have already found another couple of these objects in our sample. So this is not a single object. I think this is a full class of double-phased white dwarfs. And so this is going to be very interesting to understand why this is going on. With this, I think I'm out of time, so I'll stop here and ask the questions.
Okay, thank you very much. I hope there is I will ask Mariusz, who is on site, to lead the question session. Seeing people raising their hands.
Okay, Radek, please.
Hi, it's Radek Poleski. Thank you very much for a very interesting talk. So I have two questions. First, what is the relative mass of this hydrogen ocean that we see on the graph right now? Like, is it 10% of the total mass of the white dwarf, or maybe 1%, or maybe less?
Sorry, go ahead with the second question.
My second question is about initial final mass relation. Why there are so few points, and where do the masses come from on this plot?
Thank you for both the questions. So I'll start with the ocean one, since this is a slide. So the actual fraction, it will depend. So in this scenario of the pool, it will depend on the strength of the magnetic field. So the stronger the magnetic field, the deeper the pool. And so you can have more hydrogen, but we're talking about 10 to the minus 13, at least less than 10 to the minus 13 solar masses of hydrogen, just because if it's more than that, it would cover the entire surface. Or the magnetic field would be so strong that you would see it in the lines. So that's where we have in this scenario, that's how we get the mass of the hydrogen. But we don't actually know how big is the spot. We know it has to be bigger than about 60% of. Let me go back here. It has to be bigger than about 60% of the surface, because we do not see any helium in this phase. So it cannot be too small of a spot of hydrogen, because otherwise we would see the helium. It has to completely dominate one phase. However, the lines, we cannot really model this white dwarf very well, because there's this one problem that I actually ever mentioned, is that the lines are very weak from what you expect for a 30,000 degrees white dwarf. So the SED tells us that it's 30,000 degrees. So the slope tells us it's about 30,000 degrees. And also we do not see any helium-2, which you start seeing in white dwarfs above 40,000. So we don't see any helium-2, so we know that it cannot be too hot. But the lines are very weak. The lines are lines so weak, you usually see them on white dwarfs that are above 50,000 degrees. So there's something going on here that we are not completely understanding, in terms of there's something that is also weakening the lines. It could be the magnetic field that is weakening the lines. But it is actually still an open question, and this is why we cannot really very well model these white dwarfs, because with our models, we either get the temperature right and then we get the SED right, but we don't get the lines right, or vice versa. So I cannot really constrain the size of the hydrogen spot. So there's still some mysteries regarding this white dwarf that we still have to figure out. Maybe finding more of these objects is going to help us understand. And then regarding the other question, let me just go to the initial mass, final mass relation. So the reason why there's so few points is because, to have the initial, so let me actually go back one slide. So the masses of, so there's two masses on this plot, right? There's the mass of the white dwarf and the initial mass of the progenitor star. To get the mass of the white dwarf, we get spectra of this white dwarf, and from the Balmer lines, we can get the temperature, we can get the surface gravity, and so from that you can get a mass from the white dwarf. So we get the we get a spectra of the white dwarf. You can also just take it from models and just from the color and the temperature, but you can get much better constraints on the mass by fitting the Balmer lines, so by fitting the spectra of these white dwarfs. That's where the white dwarf mass comes from. The initial mass of the progenitor stars comes from the fact that these white dwarfs are in a cluster. So we know the cluster age because, all of the stars in the cluster are born at the same time. And so we see now the stars that are getting off the main sequence, the turn-off stars. And so we can get the age of the cluster from those stars. And so we know the age of all the stars in the cluster. And so we know the total age of the white dwarf because it's the same of all the other stars in the cluster. And on top of that, we know the cooling age of the white dwarf because we know its temperature. So we know how long it has been since it was born as a white dwarf. So if you subtract those two, total age minus cooling age, you can figure out at what age the white dwarf became a white dwarf, at what time the progenitor stars got off the turn-off, right? And so we can get in that way the mass of the progenitor star. And that's how we get these initial masses. So these are the two masses, and this is how we get them. And now to go to why there are so few points, it's because you need them to be in clusters to do this work, to do this trick. They have to be inside a cluster. And open clusters are very sparse. They're not as massive as globular clusters. Globular clusters are too old. Globular clusters, the white dwarfs will be like down here, they're like the turn-off mass in globular clusters like below 1 solar mass. So the relation is down here. But if you're interested in this high part of the initial final mass relation, then you have to look in open clusters because those are the ones that are creating massive white dwarfs right now that you can still observe. In globular clusters, massive white dwarfs are too cool to get spectra of. And so, but there's not that many white dwarfs in open clusters, unfortunately, because open clusters are sparse, and there's a lot of white dwarfs leave. They get kicks. And, even 1 kilometers per second is enough to leave an open cluster. They're barely bound. And so there's not that many white dwarfs. That's why there's so few. But with Gaia, we could find, first of all, we can find a lot more white dwarfs that are inside the cluster right now. And what we're doing to put more points on this plot right now is looking for escapers. So for white dwarfs that escape from the cluster, with Gaia, since you have proper motion, you can bring the cluster back in time and the white dwarf back in time and see and find white dwarfs that escaped from the cluster in the past. So we're finding more and more, like this is again all work in progress, but we're finding more and more of escapers to try and replenishing a little bit more this initial final mass relation.
Thank you. More question? So I don't see more question.
I see. Look at.
Okay, if there are no questions from the room, then I just have a quick question regarding you mentioned that that it's possible for single white dwarfs to go supernova 1A, right? But it's how common would that be from what you see? And could you explain again why?
Yes, sorry. I was very. It's too early for me, so I don't think I explained it very well. Let me go back. Thank you for giving me a chance to re-explain these. So, okay, what's going on is that the density inside the white dwarf is very high. And it's in the core of the white dwarf, right now, the density is above the threshold for electron capture on sodium. So sodium nuclei are capturing electrons right now and turning them into neutrons, right? Electron and a proton into a neutron. And so this is bad for the white dwarf because, the electron pressure is what keeps up a white dwarf. And so so what we did here, for example, I didn't show this red line is the same as this dotted red line, but if you include the electron capture, of the sodium already inside the core. Here we are assuming that the white dwarfs are all mixed, so the sodium is all over. but there's some of it inside the core that already went to this electron capture. And so as you can see, at the same radius, you have a smaller mass that it can sustain, right? With respect to the normal, because you have less electrons, right? You have less electrons, and so at the same radius, you can sustain less mass, or at the same mass, you have to go smaller in radius to sustain the whole mass of the white dwarf. And so right now, the sodium is still mixed because the white dwarf is young, and so it hasn't had enough time for the sodium to sediment all the way into the core. But as more and more sodium sediment into the core and more electrons get captured, you can have the white dwarf can keep actually shrinking until you might reach the second threshold, which is the threshold for double electron capture on magnesium. And then if you have double electron capture on magnesium, then you're gone, because you just keep shrinking until there's no more electrons. The Chandrasekhar mass becomes very small, and so you collapse. And so, yeah, that's why I was saying, you have the collapse. And what happens after the collapse is not sure, it's not clear, because you can either explode or, become a neutron star. We still don't know, because there's these other possibilities that have been proposed of accretion-induced collapse. So when a white dwarf accretes more mass, it can collapse and become a neutron star. And this is a very similar scenario, except that there's no accretion. So a white dwarf may collapse and become a neutron star, like in the accretion-induced collapse, or it can explode into type 1a supernova. That depends on the dynamics of the oxygen burning in this case. And how common is this? I haven't actually computed the rates, because I didn't want to get too much into this, because I'm not. If I had to bet, I would say that this white dwarf will not collapse because it will freeze. The core will freeze much quicker than this. The sodium takes a lot of time to sediment, and the white dwarf core might crystallize way before then. And if it does, it's fine. The white dwarf will be stable. But if it does collapse, this white dwarf is only 40 parsecs away, so it's extremely close, which means that this would be a common way to create a type 1a supernova or a neutron star. And we are talking about probably 10% or 20% of the total population. Like, we're talking about like a big fraction of the total population, which I would have to compare. I remember like doing some rough calculations, and that was what I found. But I didn't want to get too much into it, because I think it's very speculative. I'm not saying that there's a lot of type 1a coming out of these. It's just a possibility.
Okay. Thank you very much. Thank you for your talk. And I think we have to stop here. People are getting impatient. So thank you very much for your talk. Let's do the clapping and thanking our speaker again.
Well, thank you for coming and having me there.
Thanks and bye. And thank you all for joining. And I'll stop all the streaming and